very difficult to begin after an introduction like that. All I'd like to say to start with is that I came to the Science Gallery in January to review an exhibition called Visceral. And while I was here, I got chatting to Michael John Gorman, the director of the gallery, who was very kind enough to invite me back to give this talk after I strong-armed him about why my book wasn't on sale in the gallery's bookshop. So I'm pleased to come here and talk to you today. My job's made quite easy, despite the lovely introduction, and it's made quite easy by the picture that you're seeing on the screen behind me here, because really it's my book Quantum is about the people in this picture, and it was this picture that I saw when I first saw it. I was 16 years old. And I looked at this picture, and there were people in it I was familiar with. And I put it up there deliberately to get you all to have a look at it as you were getting seated and waiting for this talk to begin. Because in this picture, there's people like Albert Einstein, Mary Curie, people we've all heard of, Erwin Schrödinger from Schrödinger's cat fame, Werner Heisenberg from the uncertainty principle. And this picture was taken in October 1927 in Brussels. And it was at the 5th Solvay Conference. Now, the Solvay conferences originally began in 1911, and they were held every few years. And physicists would come together, an international group of physicists would come together to discuss a particular topic, a particular theme. And in 1927, they'd gathered to discuss electrons and photons in Brussels. And when I first saw this, I thought, what are all these wonderful people doing there? These names from the history books that I, even at 16, had come across in physics. And so I began to sort of dig around, and I realized that, in fact, everybody who had a leading role to play in the beginnings of quantum physics was at this conference. And I always thought that this would be a wonderful way, by looking at the personnel in this photograph, and this photograph as a beginning, of unfolding the story of the discovery of the quantum and the debate between the two the 20th century's most famous physicists, Albert Einstein, there, who's in the middle, front and center, and Niels Bohr, who's just there in the second row, at the right at the beginning, on the right-hand side, because there was a debate that began between those two at this conference, and it was about the nature of reality. What was quantum physics saying about reality? So that's where my interest began there. This is probably one of the greatest gatherings of minds in history, I think. I can't quite recall precisely, but 17 to 19 of these people went on to win a Nobel Prize. I think there were 26, 27 people invited to the conference. And there's only one woman, she's sitting there in the front row, and that's Mary Curie. And she's the only one of the lot who had two. She won one for chemistry, and then she won one for physics as well. But my story, and the story of quantum physics, actually begins with the chap on the left-hand side of the front row, Max Planck, holding his hat there. Now, in 1900, Max Planck was 42 years old, and if you look at him, he doesn't look like a revolutionary. He looks like a Prussian civil servant, but he seems to be the right man in the right place at the right time, and that place was Berlin, or Germany more broadly, in 1900. Because for the best part of a decade, German scientists had been conducting ever more, refined measurements of the problem of the black, the problem of the hot iron poker. Because we all know that if you put an iron poker into a fire, it sort of glows a dull red, then a cherry red, then sort of an orangish colour, then a whitish bluish colour, depending upon the temperature of the fire and the temperature to which the iron rod's been heated. Now, what German scientists were doing in the 1890s, what they were effectively trying to do, was to work out what was the relationship between the colour of a hot iron poker, the intensity of light of the hot iron poker, and the temperature at which it was, and its temperature. It seems like a sort of, out-of-the-way problem, given that in the 1890s, X-rays were discovered, radioactivity was discovered, and the electron was discovered. So most of the world's leading physicists elsewhere had been dashing off to their labs to do do experiments in these three new emerging fields of electron physics, X-rays, and radioactivity. But Germany's leading scientists, experimental scientists, were basically making high-tech ovens. they were making high-tech ovens because one way of sort of simplifying the problem of the hot iron poker is a thing called black-body radiation. Physicists try and simplify, however simple a problem is, it's often quite complicated to model mathematically, so they try and simplify it. So one of the things they did was to imagine effectively a high-tech oven. Because what they discovered is that the relationship between the intensity and the color and the temperature, I call it a hot iron poker, but if you think about if they could simplify it to an object called a black body, it didn't matter what it was made of. So they could get rid of thinking about the hot iron poker being made of iron and simplify it by just thinking it was some sort of material, special material. And what they were trying to do was when they heated it, it would start glowing, sort of red, orange, blue, white, and then in the invisible part of the electromagnetic spectrum. And all that radiation would be stuck in inside the box. There'd be a little hole in it, and they would sample the radiation. And what they were trying to do was to do what's in the picture there behind me, that curve, that sort of shark's fin. They were just pulling out the data points and just plotting them and see what they got. And what they wanted to do was to come up with an equation that could reproduce those curves. In October 1900, Max Planck had invited a friend round for dinner, and that friend had been one of these experimentalists involved in investigating black-body radiation. He said to Planck that we've got some new data, and could Planck make any sense of it? Planck wasn't an experimentalist, he was a theorist. And he was pretty good at maths, he was pretty good at thermodynamics, the science of energy and heat in motion. And after he put his 4 children to bed, he had the raw data, he had the curves there, and he started to play around with the mathematics. And after a few goes, he came up with an equation that allowed him to reproduce those curves. And that's the sort of thing he came up with. That's a sort of a modern version of what he came up with. I wanted to say to you one thing, which why were these German scientists interested in this problem? They were interested in this problem because in the 1890s, Germany had only been Germany since about 1870, 1871, after a war with France. And Germany quickly wanted to establish itself as a European and a world power. And the technology that was driving things then was electricity and electrification. And the leading figures, the leading players in electricity and electrification were the Americans and the British. So the Germans, as they've done ever since, they were very keen on applying science and funding science and aiding science in the aid of German industry. So companies, Siemens exists today, and Werner von Siemens in the 1890s was funding, some of this research. And so the Germans were always very, very, very interested in using science to sort of aid their sort of industrial development. And why was black-body radiation important to them? Well, a black body is a perfect absorber and emitter of radiation. That's an idealization. It's an idealized body. It doesn't really exist, but theoretically, it's a perfect absorber and emitter of radiation. When you're making light bulbs, what you want to do is get as much light as possible and as little heat as possible. So what was driving this research in Germany was the Germans' desire to make better light bulbs, right? Because if they could minimize the heat that was being generated and maximize the light, if they could come up with the solution of the black body problem, they could have a way of calibrating light bulbs and therefore making better light bulbs than their competitors. So the origins of quantum physics and the quantum actually come out of this German desire to match and overtake their British and German counterparts in the electrical industry. Now, what Max Planck discovered was a formula that allowed him to reproduce these curves, but it was just a formula. Right? He gave a lecture pretty much like this one to his contemporaries in Berlin in October, but he didn't understand the physics. He didn't understand what it was telling him about the underlying physics. What was the guts of this equation? So he spent the next 6 weeks trying to derive his equation. Rather than just put it together, bits and pieces, so it just worked, so he could reproduce his curve, he tried to derive it. And what he found was that when he derived these things here, this equation here, it was this thing, this number, this thing that we now call H here. All the others don't really worry about the rest, but it's this guy H here. What he found was that H was a number. And it was that, just concentrate on that 0.000. That's, as I say there, 6.625 divided by 1,000 trillion. Almost zero, but not quite. And so what Planck found was that if he couldn't make it zero. If he made it zero, if he made that h go to zero, then he couldn't reproduce the curves, right? And basically what he had to do was to make his equation work, was to say that energy came in chunks, right? It was absorbed and emitted in this process of radiation being exchanged in a black body in packets. And the word quanta comes from that. And but he believed that energy was continuous, a bit like sea waves, or and that in his derivation it just so happened that it would work, if he sliced and diced it. And he sliced it with this h, this little number. This little number was like the axe that was chopping up these sort of what was previously continuous energy. But he thought it was a mathematical trick, because if any of you have done and suffered calculus, you know that in calculus we're always sort of slicing up the area under a curve into sort of ever thinner strips, and the thinner the strips, sooner or later you can sort of magically make them join back up together again. So he thought he was doing the same sort of thing, just a mathematical trick, no physical basis there, and it had come out in the wash. As much as he tried for many years to try and make H disappear and get rid of these packets of energy that were being absorbed and emitted as he managed to get his curves sorted out, he couldn't. And he admitted defeat at the end and said he had to just learn to live with the quantum. So by 1905, for 5 years, no one really had paid much attention to the quantum. They'd seen it as a solution to the black body problem. Germany was making better light bulbs, but everybody ignored the packets of energy that Planck had stumbled across. He was very much a reluctant revolutionary. And it was Albert Einstein, and this picture is taken from about 1906, 1907. It was Albert Einstein who, when he came across the work by Planck, who was the first person to take it seriously. None of Planck's contemporaries in the great universities of Cambridge or Göttingen, but Einstein, who at the time I'm sure most of you will know, was a patent clerk in Bern, Switzerland. And of course we're familiar with the old guy with the hair and his tongue sticking out. This is the younger Einstein. And the second picture is, there's Einstein there, and this is with his sort of schoolmates. He's about 17 or 18 there. And it was Einstein who takes the idea that energy can be sliced and diced and comes in chunks seriously. And he said he felt like the rug had been pulled out from underneath him. And with nowhere to build, or, physics was, on very, very shaky grounds. This was in 1902. So for 3 or 4 years, he thought about what Planck had done, and he believed that what Planck had done wasn't quite correct, right? Now, when I do physics, and I'm sure some of you guys who are here from Trinity College Dublin, when I do physics, often we're told that, Einstein did this, or somebody did this, because this was a problem. So here was an experiment that nobody could explain. They came up with an idea to explain this experiment. Well, Einstein did it slightly in the reverse way. He had a look at what Planck had done, and Planck had been forced to accept that energy had been sliced and diced in his derivation. And it was sort of a cack-handed, sort of inconsistent sort of derivation. And people were happy with it because it did the job that people wanted it to do. Einstein, on the other hand, decided he could reproduce Planck's famous formula by treating light as if it was a gas. And that's what he did. He managed to achieve a derivation of Planck's formula by just treating light as if it was made up of particles. And that was really revolutionary. In fact, Einstein later said that the fact that light is made up of particles, his quantum theory of light, it was the only revolutionary piece of physics he ever did. Now, this is from a man who did special relativity and general relativity, and the one thing he says is that it's the quantum theory of light that's revolutionary. The fact that light is made up of packets. And unlike Planck, he's not saying that these are, it's continuous and it gets sliced and diced when things are emitted and absorbed. He says light is just made up of particles, right? And so what he did, after coming up with that, he had a problem, because for over 100 years, the prevailing view about light was that it was a wave. And there's a famous experiment done by a guy called Thomas Young in, I think, about 1801. when he has a light source, this black dot, and there's a screen through which the light passes. As it passes, it sort of spreads out. There's a screen in front of that with two holes in it. The light passes through both these holes, and the waves of light, if you like, overlap. And that causes, on the last final screen, a pattern of light and dark, what we call fringes. Very much like two pebbles being dropped into a pond and the ripples sort of spread out. And where there's a peak, the peaks reinforce each other. Where a trough meets a peak, they cancel each other out and stuff. That can only be explained, this experiment can only be explained, the Young's two-slits experiment, if light was a wave. So Einstein is now postulating that light is made up of particles, but for a century everybody's believed that light's been proven to be a wave phenomena. But Einstein says that there's a piece of physics, there's an experiment in physics that no one's been able to explain, and it was called the photoelectric effect. And it sort of, plagued physicists for a decade or more. And what it boils down to is this. Imagine you've got a metal surface. If you shine a beam of light onto it, electrons are emitted from this beam, from this metal surface. Now, if you tried to explain it using classical physics, a wave theory of light, what people assumed was that the more intense your beam of light that was being shone on a table, the more energetic the electrons should be, because they were being given more energy. But Einstein was able to explain that, in fact, actually what happens when you increase the intensity of a beam of light, you're increasing the number of photons, these particles of light that make up the beam. Therefore, more of them are hitting the metal surface. Therefore, more electrons are being emitted from the metal surface. No one still didn't believe him. And people try and tested his formula. That thing up there is a graph of the kinetic energy, the energy of motion of an electron, on the what we call the y-axis, and on the x is just the property of the energy of the photon minus the minimum energy of the metal. So, but it's always a line like that. Now, Einstein was awarded a Nobel Prize for this work in 1921. He was awarded a Nobel Prize for that equation, EK is equal to h nu minus phi. But not for his explanation. So they said, we've tested your formula reproduces the data, but we don't accept your underlying explanation that light's made up of particles. So by 1905, where are we? We have Planck who discovered the quantum, but he just, he reluctantly accepts it. Most people ignore it. They think he's just saying that energy is sliced and diced. In certain instances of being emitted and absorbed when radiation meets matter. Einstein comes along, he extends the quantum theory by saying that there's a quantum theory of light, light's made up of particles. And the next great contribution to the development of quantum physics is by this chap in the first picture. You can't really see him, I've just stuck him in there because that's a guy called Niels Bohr, who you can better see is the chap who's on the right-hand side in the second picture in the top right. Niels Bohr was a Danish physicist, and he came to Britain in 1911. He came to Britain in 1911. At that time, 1911, Einstein is a professor, I think, in Prague. He's world-renowned for his theory of special relativity. General relativity hasn't been published yet. That's something that's going to happen in a few years. But from being a patent clerk, Einstein's shot up the academic ranks, and he's now a professor of physics in Prague. Niels Bohr, at this point, is a postgraduate student. He's on a year scholarship to Cambridge, funded by the Carlsberg Brewery in Copenhagen. And he's come to work with this chap who's underneath there, this chap here. That's J.J. Thomson, because in 1911, Niels Bohr was very keen on electron physics. He'd done his PhD in electron physics. Electron physics was one of the thriving areas of research in the first decade of the 20th century, and he wanted to go and work with Thomson. Thomson was head of the Cavendish Laboratory at Cambridge. Unfortunately, they never hit it off because Bohr's English was poor. He learnt it by reading Dickens, and J.J. Thomson, Sir J.J. Thomson by this stage, I think, was a real, he was a mathematician, he was an experimenter, but he was also a 19th century gent, and he didn't take kindly to Bohr pitching up in his office, pointing to a book and saying, you're wrong. So they never hit it off. But Bohr went to work for this chap here, who I'm sure some of you will recognise, that is Ernest Rutherford. And in 1911, Ernest Rutherford was head of physics in Manchester. He'd come down to Cambridge to be a guest of honour at the research students' dinner. Bohr met him, liked him. Now, Rutherford is a New Zealander. He has a Nobel Prize because he's for chemistry, and he hated chemists. And he got a Nobel Prize for chemistry because he was one of the people who came up with the fact that radioactivity is a transformation of elements. He'd come up with alpha particles, beta particles, gamma rays. He'd spent a long time working on radioactivity, and he'd made his reputation there. And he'd set up a group in Manchester who were pioneering, new radiation experiments and using alpha particles. And one of the things he'd done in 1911, Rutherford, he'd come up with, ignore these arrows for the moment. What Rutherford has come up with is the model of the atom that we all understand, what we all learn at school, the one where we have a central nucleus around which electrons go, a bit like planets around the sun. The problem for Ernest Rutherford in 1911 was that classical physics says that if you have electrons going in a circle, they're negative charges, and if you go in a circle, they will radiate energy and slowly spiral into the nucleus. Not slowly, but they will rapidly spiral into the nucleus. So if you have a nucleus with an electron going around it, Rutherford's atom would collapse, even though Rutherford's atom seemed to support all the data that his group in Manchester had been collecting by firing little alpha particles at very thin pieces of gold foil. Now, what people expected is that most of these alpha particles passed straight through, but some of them were coming straight back. The only way they could understand that was if the atom had a sort of very heavy central core, and these alpha particles were just being bounced back from there. So it seemed to make sense of the data, but it couldn't exist because these electrons were going to spiral in, and then the atom would collapse. It was Bohr who fixed this flawed Rutherford atom. It was Bohr who took the quantum into the atom, because what Bohr did, he did something very simple. Daring, revolutionary, but simple. He said, look, in an atom, there are only certain permissible orbits for electrons. Right? So, an electron cannot just orbit anywhere, cannot have any orbit it wants. It can only have certain permissible orbits. So, in a sense, he quantized. So, this is one of the ideas in quantum physics. Whereas things in the past have been continuous, everything, like energy, now they were coming in chunks. And again, in the atom, instead of having any orbit, only certain ones were possible. If the electrons were in these permissible orbits, they couldn't collapse. They were just prevented from collapsing by Bohr as a sort of condition. There's mathematics to back it up. He just didn't make it up. He backed it up with some mathematics. And then he backed it up with the available experimental data. This is over a period of a couple of years, because these arrows that you see from these different energy levels or electron orbits are the electrons in the famous quantum jump. The quantum jump, and that being an electron in, for example, the outermost ring there, the arrow, and going down to the next ring is an electron jumping between two different orbits or energy levels in a hydrogen atom. And what happens then is that a little photon of light is given off, and you can get these what are called spectra, and each element has a unique fingerprint of light. And Bohr, by coming up with the idea that of the quantum atom, that only certain orbits were permissible, could explain why each element had an individual light fingerprint, because each element had these unique series of possible electron jumps from one orbit to another within a particular atom of a particular element. So by the 1920s, what we have is Planck, Einstein, and Bohr having discovered the quantum, come up with the quantum theory of light, introduced the quantum into the atom. But physics, there's no coherent structure. Quantum ideas and the ideas of discontinuity, that things can come in bits, they're not continuous, have been sort of added ad hoc, bolted onto classical physics as a particular problem demanded or a particular area of physics. There was no coherence. There were no sort of Newton's laws of physics for the emerging quantum physics, and they desperately wanted that. By the early 1920s, Bohr became the director of his own institute in Copenhagen. And that became a focus for some of the most talented young theoretical physicists who he began to gather around him to begin to work on some of these sort of problems. By 1924, I say 1924 because a couple of things happened in 1924 that are pivotal to the story of the development of quantum physics. One is some work done by Compton, Arthur Compton. Arthur Compton was an American experimental physicist. In 1923-24, what he did, he took some X-rays and he shot them effectively at electrons. And what he found was that these X-rays behaved like billiard balls bouncing off of a billiard ball bouncing off another billiard ball. And that was the first sort of direct evidence that people would accept that light, because light is a part of the electromagnetic spectrum, X-rays are at one end, light's sort of in the middle there, that light was also made of particles, Einstein's fabled sort of photons. So Einstein's been saying this since 1905, but it's only in 1924 that people begin to accept a quantum theory of light. And Compton wins the Nobel Prize for this work called, and it's a turning point. Einstein is no longer sort of one of a handful of people that believe in the quantum theory of light. And the other is if I've got him up there, no, I haven't got him up there, is this chap here. Now, his name is Louis de Broglie, and he was a French prince and a German duke, right? But also a rather fine physicist. His brother was a physicist, and his older brother was a physicist, and he, I think, served out the First World War as a radio operator at the Eiffel Tower, and after the war continued pursuing his passion for science and physics, even though I think he came from a long line of generals, French generals and courtiers and diplomats. He's the chap who comes up with the famous wave-particle duality. Yeah. Because what we have is that, since 1901, we have loads of experiments, but Young's Young's two-slits experiment shows that light is made up of waves. There's loads of experiments out there that show that, light is made up of waves. Then you've got Einstein coming up with his quantum theory of light and explaining experiments that couldn't previously be explained by postulating that it's made up of particles. The French prince comes along, he says, well, look, we could extend that to all matter. Well, why does it have to be confined to light? Why can't electrons, which have traditionally been regarded as particles, why couldn't they have wave properties? Why couldn't electrons be particles, waves also? And so that was the famous wave-particle duality. And when he wrote this up as a thesis in 1924, no one knew what to make of it in Paris, so they sent it to Einstein to ask him what he thought of it. And Einstein's response was very simple. He said that de Broglie had lifted maybe a piece of the veil that had been hiding what nature was really like. And so we now have another sort of piece in the sort of quantum jigsaw, wave-particle duality. Now, we're now in 1925, so we've got the quantum is now established. The quantum theory of light is now established, and Einstein's been vindicated, and we've got the quantum atom. And the quantum has been used in all sorts of other areas in physics, but not in any sort of coherent, logical way, just ideas bolted together to make things work in a very ad hoc fashion. So there's a real desire for a quantum mechanics, a bit like a Newtonian mechanics, something that will bring coherence and structure. And these two chaps are the ones who do it. That's Werner Heisenberg on the left. He was sort of the wunderkind of German physics. I think he was 23, 24 when he came up with matrix mechanics, which is a form of quantum mechanics. Time means that I can't really sort of go into too much detail, but the thing about matrix mechanics that Heisenberg discovered while he was suffering from hay fever in a sort of desolate small island in the middle of the North Sea was that it's a very abstract form of mathematics that physicists at the time weren't used to. Now it's taught at A-level, and it's taught in first year undergraduate maths and physics courses. But at the time, Heisenberg stumbled across matrix mechanics. And it was the chap on the right who came up with wave mechanics, Erwin Schrödinger, who I think, somebody will correct me, but I'm sure he was here for a very long time at Trinity College Dublin, or at the Institute for Advanced Studies. I'm not sure, but he was in Dublin. He was knocking around in Dublin for a very long time. He, a few months later, 6 months later, so after having, struggling to come up with a quantum theory of quantum mechanics, within 6 months there's an embarrassment of riches. There's two theories. There's a matrix mechanics and there's a wave mechanics. Now, the difference between the two is that Schrödinger's wave mechanics was very friendly because people were used to, physicists were used to dealing with wave equations. They were used to doing, using differential calculus and thinking in very sort of 19th century sort of mathematics, but whereas matrix mechanics was something that was very new and alien to them. And it seemed to be like there were two different theories, but it was proven very quickly, including by this chap here on the right, Wolfgang Pauli, that these two theories were two sides of the same coin. So even though Schrödinger often talks about waves and a wave function, and Heisenberg was talking about matrix mechanics, these two different mathematical formulations embody the same physics. And at different instances, one was easier to work with for certain problems, as opposed to another. But for another problem, you might want to use matrix mechanics as opposed to wave mechanics, but they were equivalent. Now, there's a thing that many of you might have heard of, and it's called the wave function. And the wave function is something that comes out of Schrödinger's wave mechanics. And it's a bit like, if you were trying to model water waves or ocean waves or something, you have a wave equation. This is one of the things that people threw at the wave-particle duality. Schrödinger stumbled across the wave equation. He was working on a wave equation and came up with wave mechanics because he'd been asked to present a talk on wave-particle duality and to explain de Broglie's ideas. And when he did it, afterwards, somebody said, well, where's the wave equation? If electrons can behave like waves and particles can behave like waves, what would be the wave equation? So he came up with this equation. And there's a thing in there called the wave function. It's just like a solution, if you like, of this equation, Schrödinger's equation. And it's not Schrödinger tried to interpret it. What was this wave function? He thought it was some sort of real entity, some sort of density of charge or something in relation to sort of particles colliding or something. Until Max Born, the chap on the left, came along and said, no. What the wave function, Schrödinger's wave function in wave mechanics does, it gives you probability. It's sort of like a probability wave. It's not a real thing. It's a bit like a crime wave. Someone's used this example before. There are individual crimes, they're real things, but a crime wave is a bit more of an abstract concept. And so the wave function was this sort of abstract concept that you could manipulate to give you real numbers, real things. But what it gave you was the probability of something. So if you were colliding, say, two particles together, or you wanted to measure a particular particle, what the wave function would do, once you'd manipulated it, it would churn out the probability that it would be here rather than there. Right? And so once you did an experiment, you would find it either there or here. It just depends. If you did it a number of times, you might find it 10% of the time over there, 30% of the time over there. But it was just giving you the probabilities of where it might be. So that was a big shift, because in the past, in classical physics, you do an experiment. If you know the various factors, you can make definite predictions about the outcome of a particular experiment. But now probabilities were being introduced to where things may or may not be. The next great leap is in 1927, when Heisenberg comes up with the uncertainty principle. Now, 1927 is a very interesting year because for about a year or so, you've had two theories of quantum mechanics, wave matrix mechanics, that have been shown to be just two different mathematical descriptions of the same physics. And you've got this, and people have been trying to work out, what is this wave-particle duality? So Niels, Bohr and Heisenberg have been locked together for a period of about 6 months in Copenhagen on a daily basis, struggling to try and make sense of what is wave-particle duality, what is physics, what is quantum physics telling us about the nature of reality. And they both are getting a bit on each other's nerves, close proximity, sort of toying with these ideas. So Niels Bohr, buggers off to Norway. He buggers off to Norway for a couple of weeks of skiing, leaving Heisenberg on his own. And Heisenberg, while he's left on his own, hits upon the uncertainty principle. What the uncertainty principle boils down to is that if you have a particle, you can measure its momentum or you can measure its position with 100-degree accuracy. Right? You can measure one or the other right? The better you know one, the less you know about the other. So you can't do, in classical physics, you can know the position and the momentum of a particle with 100% accuracy. Heisenberg comes along with his uncertainty principle, and there it's encoded in mathematics, says that there's a limit to the degree to which you can know both. And you can't, the more you know about one, the less you know about the other. While Heisenberg's coming up with the uncertainty principle, Bohr, by skiing, comes up with the principle of complementarity. He says, look, you know what? It seems to me that there are experiments, Thomas Young's two-slits experiment, the photoelectric effect experiment, when, depending upon the question, i.e. you ask of nature, the experiment that you perform will give you, depending upon the type of answer you get. If you ask nature wave questions, then you're going to get wave answers. You're going to get those fringes on the screen on a slits experiment. If you ask nature sort of particle questions by shining a beam of light onto a metal surface, you're going to get particle answers with electrons being shot off. You shouldn't find situations when you're going to, it's one or the other, was the way he was looking at it. And so he saw them as two complementary aspects of the underlying reality. And so by 1927, we end up with what begins to be called later, not then, but later, the Copenhagen interpretation. And the components of that are Born's probabilistic interpretation of this wave function that Schrödinger has come up with in this equation, that you're not predicting things, definitely will be somewhere. All you can do is predict their probabilities with certainty, if you like. There's 30% certainty that a particle may be there. Heisenberg's uncertainty principle, that you can know something, the more you know about the momentum, the less you're going to know about its position. And if you want to really know it 100%, you will know nothing about the other. Bohr's complementarity. And this idea of the collapse of the wave function. Now, this is a quite interesting thing. The idea would be that if you've got a box, and in the box there's a particle. Oh, I should rephrase that. Copenhagen would say there's a box. If Copenhagen would say that there is no box in that particle. Sorry, there's no particle in that box with a position until you do an experiment to measure its position. So it could be sort of smeared all over that box. And until you do an experiment to actually measure it, and therefore collapse the wave function, which sort of embodies the possibilities of all the sort of positions it could occupy in that box, there is no particle with a definite position until you do that. So these are sort of the four components of the Copenhagen interpretation. So for them, there's no quantum reality beyond, that's been revealed by an act of measurement or observation. And so, as I say there, for them its meaning is to say that an electron exists somewhere independent of an observation. And that's the Copenhagen sort of interpretation. And that's 1927. Bohr sort of goes to a conference in Como, Italy, 1927, and he puts forward the Copenhagen interpretation. But they're all there, except for, Schrödinger's not there because he's just been appointed professor of physics in Berlin, so he can't come. But Einstein isn't there either. Einstein isn't there because he doesn't want to set foot in fascist Italy. So the one person he wants to convince, because Heisenberg's convinced, Pauli's convinced, all the other people that that Bohr might want to convince, they're already convinced. They're already his sort of assistants or members of what later some people would call and I agree, the missionaries of the Copenhagen interpretation. The one person he really wants to convince is Einstein, and Einstein's not there. But a month later is the conference in Brussels, right, in 1927, a week-long conference looking at electrons and photons. What happens at this conference is that each one of these, the leading players, Heisenberg, Schrödinger, Compton, all these people give papers. They give papers, and there's Q&As, and that happens for about 3 or 4 days. Einstein doesn't give a paper. In fact, Einstein speaks twice in this conference. Once to make a small point and once to ask a question. And a lot of people know what Bohr has come to the conference to do. He's come to the conference to convince Einstein of the Copenhagen view of quantum reality. So they were interested to see what Einstein's going to say. Einstein doesn't say anything. Fortunately, they've closeted all the participants together in a hotel, a lovely hotel called the Hotel Metropole in the middle of Brussels. So every morning over the conference, over breakfast, there's Bohr sitting there with Heisenberg or Pauli. Einstein saunters in, and he goes over and he comes up with a thought experiment. He's conjured up a thought experiment, an imaginary experiment, using perfect instruments and everything, in which he tries to challenge the Copenhagen version of events. What he wants to try and do in these thought experiments, he's trying to say, look, I can do something which you say I can't do in these imaginary thought experiments that I'm constructing. So he comes down pretty much on a daily basis, one of these. So every morning he pitches up, he's conjured up an experiment. In the course of the day, Pauli, Heisenberg and Bohr get together and they were able to refute Einstein's thought experiment that's attempting to undermine this Copenhagen interpretation of theirs. And that's a picture a bit later on, but that's the sort of thing that was happening then. And it was the beginning of a 30-odd-year debate, this conference in 1927 between Einstein and Bohr, because of the two men's different philosophies. For Einstein, he believed in an observant, independent reality. He believed that the moon existed if you didn't look at it. Right? He believed it was a job of the scientist to uncover that independent reality. And one of the ways he judged quantum physics was to think, well, okay, it's a good theory. It's maybe the best theory that we've got, but maybe it's not the end of things, you know. Because he had a philosophical worldview which he used to judge that theory. He believed there was an independent reality. So he sort of, in a way, had his philosophical foundations on which he constructed his scientific theories. Because he believed that, obviously, in the future, if you're... It happened to Newton, you know, with gravity, when general relativity came along and sort of superseded it. It's still a part of, you know, the physics, but Einstein, you know, sort of encapsulates Newtonian gravity. That, you know, your theories of physics can be proven to be, you know, wrong or need adjusting. But it leaves your philosophical sort of base intact. So for Einstein, the philosophy came first and the physics sort of came second. For Bohr, he seemed to do it the other way around. He constructed a worldview, the Copenhagen interpretation, of an observer-dependent reality. He sort of said, look, he was using his physics to sort of construct a philosophical worldview. So the two men had two very sort of different approaches to this. This is a light box. This is a famous experiment, thought experiment, that in 1930, 3 years later, Einstein showed up in Brussels. He saw Bohr and smiled and then unleashed this new thought experiment. This new thought experiment was... very, very briefly, because I'm running out of time. This thought experiment is very, very interesting. It shows you the depth to which Einstein abhorred the Copenhagen interpretation. But also, he felt that it was a sort of a bit of a fetter on physics and the influence it was having. Because this is what happens in this experiment. Einstein says, look, take a box of light. In the box, there's a clock. And there's a shutter. But there's also a clock on the wall of the lab, which is synchronized with the clock in the box. The shutter opens at a given time, so he knows the time at which the shutter's opened, and the shutter shuts. And at that point, what he does, because he's done it before, at the beginning he measures the box, so he knows its mass. He measures it after. And from his famous E is equals mc squared, where E is the energy, m is the mass, c is the speed of light, Einstein says, look, I can tell you what the energy difference is. And if I just scroll back a couple of, if I can just do that quickly, that bit here, there's two forms of the uncertainty principle. When I've talked about, you could know this a particle's position and momentum, you know one or the other with 100% accuracy, it's this one. But it all can be recalculated in terms of energy and time. So what Einstein is trying to show in this light box experiment of his is that he knows the energy because he's measured the box and he measured the box again, and he knows the time at which it happened. And apparently, people say who were there at the time and witnessed it, Bohr looked like if he'd taken a thrashing from his master, looked like a dog who'd taken a thrashing from his master. Bohr was completely dumbstruck. He didn't know what to do for the rest of the day. Here's a picture, I think, taken at that conference where Bohr is chasing Einstein down the street, I think, and you can see that Einstein sort of got a whimsical little smile on his face. Because at that point, Einstein seemed to have got found a little dent in the Copenhagen interpretation. Until Bohr, this is a later diagram drawn by Bohr. Bohr says he spent all night taking apart this box of light, putting it together, and then he had a flash of inspiration. Einstein so wanted to take apart the Copenhagen interpretation, that Einstein forgot his own theory of general relativity, right, in coming up with this thought experiment. Because when the photon of light leaves the box shifts its position in the gravitational field. And that affects things enough that the uncertainty principle stays intact. But Einstein had forgotten the general theory of relativity, right? So that, to me, it sort of summed up the sort of intense emotions, if you like, and desires involved amongst these two men. And it was a friendly rivalry. It wasn't bitter. It was a friendly rivalry, but about big things. It was about the nature of reality and the direction of physics and what have you. And there are very few pictures of these two men together, and they saw each other hardly at all. Various conferences, they communicated via friends. Einstein was a loner, who in 1933 went to America, ended up in Princeton. Bohr was the director of a centre where he had people like Pauli as assistant, Heisenberg as an assistant, and people from around the world to come, and were later on, left and went off to sort of promote the Copenhagen interpretation. This is the famous Schrodinger's cat for Professor Love. I'm going to have a quick look at that. Schrödinger wanted to show up the absurdity of the Copenhagen interpretation. In fact, Schrödinger's thought experiment, cat experiment, was inspired by a dialogue between Einstein and Schrödinger. And it's in the book because the original thought experiment that the two men were discussing involved exploding powder kegs and things like that. And so this is what happens in Schrödinger's cat. There's a cat, there's a vial of poison, there's a hammer, it's all in a box, and at some point there might be a radioactive decay, the hammer breaks, the vial of poison is dispersed, and the cat dies. But not looking in the box, you don't know. So Schrödinger says, together with Einstein, there's a cat in a box. It's either dead or alive. End of story. It's dead or alive. We look and we find out what it is. Copenhagen, that's Bohr and Heisenberg, they say, well, look, there might be a cat in the box. It might be a bit dead, or a lot dead, or a little dead, or dead. We just don't know. This cat is in sort of a quantum purgatory of states. And until we open the box, that act of measurement or the act of observation, when it collapses, the wave function of the collapses, and all these potentialities and possibilities have become one actuality. So there is no cat in the box, which is dead or alive for the Copenhagen. For Einstein and Bohr, there is a cat which is either dead or alive. And that's all Schrödinger is trying to show is the absurdity of the sort of Copenhagen position. That's what it is. I just want to finish very, very briefly by having a look at something that, as I said in the introduction, about particles being on opposite sides of the universe that can sort of influence each other. Because the third time that Einstein really threw a direct challenge at the Copenhagen interpretation, one was 1927 during the week-long conference. He was rebuffed. One was in 1930 when he made that error in his desire to crush Copenhagen. And in 1935, around 1935, he came up with two colleagues at Princeton, two younger colleagues at Princeton, Podolsky and Rosen, a thought experiment, a new thought experiment. And it's known as, EPR. And it sort of goes along a bit like this. It says, imagine you've got a particle A. Imagine that particle sort of decays into two particles. Because you know something about particle A, and the other two are entangled, connected with it, Einstein said, I'll tell you what I can do. We've got two particles now coming from A, B and C. I don't know the position of B, but I can measure its momentum, right? But because the momentum of C is entangled, connected, because they sort of related together in A, I can calculate the momentum of C, and I can now measure its position. I know two things about C. I've measured one, and I've calculated the other. And that, Bohr and his contemporaries said, was like a bolt from the blue. This is in like 1935. And Bohr never really was able to counter Einstein's argument. But also Einstein, by 1935, was also becoming an increasingly isolated figure. Things had moved on. People were much more interested in particle physics, not in quantum physics so much. As often happens even today, it's shut up and calculate was sometimes the advice of people. And being worried about the interpretation of quantum mechanics was seen to be a sort of an old man's game. And Einstein died in 1955, and Bohr died in 1962. There was no resolution. One didn't say, look, yes, it's fair cop, you're right, and I'm wrong or anything. I haven't got a slide up of it, but when the night before Bohr died in 1962, this is 5 years after Einstein had died, on his blackboard was a drawing of the photon light box, of the light box experiment. So, that was done in 1930. So 32 years later, he's still, the night before he died, still all playing the arguments he's had with Einstein about, the completeness and consistency of quantum physics, and maybe how he failed to sort of convince him. This experiment, EPR, this is a guy called John Bell. John Bell was an Irishman, right? I think born in Belfast, worked at CERN. In 1964, John Bell did what Einstein and Bohr failed to do. He came up with a thing called Bell's inequality, a mathematical condition, if you like, just a piece of mathematics that allowed you to choose between Bohr and Einstein. All right? If you did experiments involving sort of entangled particles, or in the experiments that were done of spins of photons spinning in certain ways, depending upon the correlation, you could choose Einstein and Bohr. And these experiments have been done. And different people draw different conclusions from them. Some people say that Bohr is right. Some people say that Einstein isn't right, but Einstein had a point. Because what these experiments show is there's something called non-locality, or dependent upon non-locality. Einstein, as a man who came up with the special theory of relativity, which said that the speed of light is a constant, and nothing can go faster than the speed of light, like the concept of locality. Yeah, that the speed of light was this sort of maximum speed limit, but also event A requires enough time to influence event B over here, this sort of idea of locality. The thing is that if you have two particles that are separated across, they could be on opposite sides of the universe, and if you know one thing about this and it goes that way and this one goes that way, it seems to be an instantaneous transmission, or info, if you like, or something. Some mysterious, Einstein called it spooky action at a distance. Or other people have called it voodoo forces and things like this. But this element of non-locality, this idea that there's not enough time between A and B for a signal to be transmitted, is the sense of non-locality. So is reality non-local? Because that's what some of these experiments have been showing up in the, even to this day. And there are various loopholes which continuously get closed off, and these are loopholes that allow people to sort of challenge the validity of some of these Bell-type experiments. The question is that what does it say for the Einstein-Bohr debate? Well, Einstein believed in an independent reality. Right? We can have an independent reality, but it might be non-local. So Einstein might have to give up something. Right? Bohr, famously, Richard Feynman said that, not Richard Feynman, Murray Gell-Mann, who's an American Nobel Prize-winning physicist, who came up with the idea of quarks. He said that Bohr had brainwashed generations of physicists over a 60-year period into believing that the job of understanding quantum physics had been done. Right? So from the 1920s and 1930s, when everybody sort of were supporting Bohr, thought Bohr had the answers, 40, 50 years later, things have changed quite drastically. And in fact, I was talking to Marcus Chown, who's the author of a book called Quantum Theory Can't Hurt You, on Friday, and I think we totted up that there are now nearly, 14 different interpretations of quantum physics and quantum mechanics, from the many worlds interpretation, which I'm sure many of you have come across, to sort of more obscure ones. So Einstein or Bohr? I'm not going to say either which one I fancy. I'm going to leave you guys to, if any of you who'd like to read the book, some of my sort of take is in there. I just wanted to give you a flavour of what I think is one of the sort of greatest sort of intellectual debates in history between two men. I think you'd have to go back to people like Plato and Aristotle and Socrates to find two contemporaries who've made contributions of that order, debating the nature of reality. Okay, thank you.
Take a seat and I'll pummel you with technical questions now. I'm a biologist. I was clueless for most of that. But what struck me, first of all, was why haven't they sorted it out then? I mean, we've had a long time, haven't we? I know it's probably
why haven't they
Is it because
out?
it's very philosophical rather than scientific?
Well, the thing is that's right. Like I said, there's 13 or 14 interpretations of quantum mechanics. Not one of them is debating the nature of the mathematics. No, not one of them is saying, well, that bit over there, that derivation right at the beginning, that's a bit iffy. Yeah, so the mathematics of quantum physics, quantum mechanics, is pretty much accepted. It's what is it saying, and
right.
It's the interpretations of it.
But as a biologist, I depend on data. and doing experiments and then coming up with an explanation, and even mathematical modelling comes into biology as well, and you're doing experiments to explain some phenomenon. Why? And it's probably a stupid question to ask, but why can't there be definitive new experiments done?
Well,
to try to reveal the system?
Well, I'll say 2 or 3 things there. Right. One, quantum physics. Paul Dirac, right? I would say Britain's greatest physicist of the 20th century, with due respect to Stephen Hawking, yeah? Dirac said that between about 1900 and 1930s, a third-rate physicist could do first-rate work, right? Why was that? Because, in fact, there was so much data that, experimenters were, people like Compton were coming up with things. There was loads of data from the 19th century in terms of the line spectra that people had already done. So there was plenty of data, and it was, Planck desperately didn't want to have the quantum. He was forced to having the quantum because the data only made sense.
Yes, yeah.
He could only get the equation that reproduced the data if he accepted that light was sort of at least part of the time, in his way of looking at it, chopped up into packets. Right. So at one level, it's always been, quantum physics has always been experiment driven. It didn't come up the other way. Sort of somebody came up with an idea and now testing at the LHC or something. It was very much driven to explain what was available.
Right.
And they explained more and more and more. And then it also got embarrassing into the mid-1920s, and 1925, 1926, into Heisenberg and Schrödinger, and of course their colleagues developed a quantum mechanics. Right? So you've got the mathematics there. Now, I'm not much sure about biology. I'm not a biologist. But once you have... So the mathematics is there.
Yeah.
Now the question is, well, what's it saying?
Right.
What is it telling us? What is it telling us about the nature of reality?
And
what sort of reality is it?
And in your book, you mention a poll that was done in 1999 of physicists and mathematicians as to which they would go for.
Yeah,
and most went for the multiverse, didn't they? They felt that was a much better more satisfying explanation. Was that the conclusion?
Well, what happens is that, I talked briefly, and, there's a lot to pack into a very short talk, but I talked briefly about the sort of collapse of the wave function. Now, forget about the wave function. It's this thing, right? Just think about it. It's over here. It churns out stuff, right? But for the Copenhagen interpretation, what's important is the act of observation / the act of measurement. Schrödinger, with his Schrödinger's cat, tried to bring a person into it, make it up, and make it an everyday sort of thing that you could get a handle on. But for the Copenhagen interpretation, it can just be a piece of machinery. It doesn't have to be a conscious, thing. It just has to be a measurement. Now, what happened in the sort of early 80s, late 70s, but mainly in the 80s, you had a new field like a quantum cosmology. Because obviously, you have general relativity, that's about a theory of gravity, it's about space-time, and it's on a huge, big scale. And then you have quantum physics, which is about physics of the small, the microscopic, subatomic. But of course, if you go back to the beginnings of the universe, well, actually, there are areas where quantum physics is now coming into play in cosmology.
Right.
Yeah. Now, Copenhagen says you need an observer or a measurement to make things happen. So how does that apply in quantum cosmology? So it was when people began to sort of do more and more quantum cosmology, and that field began to develop, questions in relation to the interpretation of quantum mechanics also became reopened after a long period when people, accepted a Copenhagen interpretation. And also there was you talk about experiments. Well, that computer there, that plasma screen up there or something, all of that, half the modern world wouldn't be as we now experience it with all the devices and everything else that we have without the quantum physics that developed earlier in the in the 20th century.
Right.
So the physics sort of works, the mathematics sort of works, right? And it sort of drives the modern world, if you like, but that doesn't mean we understand it.
No.
And
one more quick question for me before I open it up. So one of our most famous alumni was George Berkeley in Trinity, who said to perceive is to exist. I mean, he seemed to predate Bohr then, did he, in many ways? And he was a philosopher. Although, mind you, there's a better version of Berkeley. So Berkeley said that if a tree falls in a forest and nobody sees it fall, has it really fallen, But a better one is, if a man says something in a forest and a woman doesn't hear him, is he still wrong? but Berkeley, was Bohr aware of this philosophical tradition of observation, determining reality?
And the continental physicists in particular, the Bohrs, they were more philosophical anyway in terms of their sort of education, and they were more familiar
Yeah.
with these sorts of debates and arguments. And I'm sure Bohr was familiar with Berkeley.
And why were there no US scientists at this? Because it was dominated by by European scientists, I guess. I mean, the one thing Europe would love to do is dominate again in this way, I'm sure. Well, but why were the Americans behind on this?
Well, like I said at the beginning, I mean, the quantum physics originally is very much a German affair.
Yeah.
It's a German affair because of what I described about why they were doing the experiments.
Very practical.
Well, because it was experiment driven. Planck came up with the quantum against his will, as it were, because of the experiments that German physicists were doing, because they wanted to actually get a foothold in the electrical industry.
Right.
They wanted to challenge the Americans and the British, in terms of this new emerging industry. But of course, that industry was being led by Edison in America and Swan in Britain.
Yes, yeah.
And so, those guys were actually doing it. Britain and America were leading sort of the technological revolution at that time.
Right.
In fact, Einstein's father, he was a serial sort of failed businessman. His field was electrification. And electricity, and him and his brother, Einstein's uncle, that's how they made their livings. They lit up the Munich Bear Festival and stuff like that, and what have you. So, the Germans always had that sort of lead.
Yeah.
And again, it's theoretical physics as well.
Yes.
Right.
Yeah. So it's highly theoretical.
But the thing is that the Germans did theoretical physics. Right, and there weren't many places doing theoretical physics. Theoretical physics as a discipline is a really late 19th century, the real towards the end of the 19th century. I mean, it was still natural philosophy in lots of places. I mean, I think when Max Born left Germany after the Nazis came to power, I mean, Schrödinger ended up in Oxford before he ended up in Dublin.
Yeah.
Max Born came from Göttingen after the books had been burned and stuff. He ended up in Cambridge for a while, and then I think for 20-odd years, nearly 20 years, he was professor of natural philosophy in Edinburgh.
Right.
So, you know what I mean? So, I think they had it was just, the theoretical physics didn't really exist in America.
Right,
yeah. And they caught up since, but not at the beginning of the 20th century.
And one last thing from me. This is the Science Foundation Ireland funded programme. What will this mean for Irish jobs, Manjit? No, let's... any questions from the floor? Over there.
As a biologist who reads these books enthusiastically... Sorry. It appears to me they keep coming up with new dimensions, that we're in 3, 4, 5, 6. There's a dozen dimensions that these particles and these events seem to exist within. We're limited to 3 dimensions. We only can think, experiment, and do things in 3 dimensions. Is it the case that all these events, really what we're seeing is kind of side effects of things happening in other dimensions? And actually, going back to the first question, we'll never find out. We can never enter, we can conceive and theorize about dimensions, but intuitively we can't truly understand it. So therefore, we're stuck, we're imprisoned in 3 dimensions, trying to guess and formulate things that happen in dimensions that we can't intuitively even think of. So do you think maybe we'll never find out the answer because this is something which is just beyond our 3-dimensional jail, and that'll be the outcome?
Recently, in March, I met up and had a chat with Brian Greene. I don't know if many of you know Brian Greene, the American string theorist. He's got a new book out, I think, called The Fabric of Reality or something. And he's a big proponent of the multiverse. And, that's one element of it. String theory is conducted in 10 dimensions. But as the experiments are being done at the LHC, now, one component of string theory, which is in 10 dimensions, is supersymmetry. And supersymmetry makes certain predictions of particles that must exist, these supersymmetric partners. So if you think about the Higgs boson for a moment, there's all sorts of other particles that they should be detecting, right? And these energies at which the LHC operates. If they don't detect them, things like string theory, which is all couched in 10 dimensions,
and highly theoretical.
And highly theoretical, but if they find particles that have been predicted by it, that's a tick for it, if you like. So there are things you can do, but ultimately, there's always the Bishop Berkeley argument, but I think you can make progress, and you can make,
Well, I wonder, Manjit, that was my question earlier, I guess, in a way. Will things like the LHC reveal data that'll be useful?
Some people want there to be no Higgs boson.
Yeah.
Right. Some people would
not be the Higgs himself.
Not be the Higgs, but some people would be perfectly happy if there was no Higgs boson.
Yeah.
Because they think that that makes physics much more interesting.
Yes.
Yeah. That would make it much more interesting. I mean, I can't tell you how many times I've heard that over the last year or two. If there's no Higgs, great.
Yeah.
Right?
Yeah.
Not like, oh my God, we've just wasted billions or something.
Yeah.
We are operating at energies, the LHC is operating at energies at which it should be found.
Right.
If it isn't found, then actually it's back to the drawing board. That's what gets physicists
And is there a vested interest there, Manjit, in the sense that people don't want it found because it'll ruin their life's work kind of thing?
I generally don't. I think, there are
Yeah.
generally some people who think, maybe physics would be a bit more interesting if a particle that's been predicted since the 1960s that is supposed to give mass to all the other particles, and it's at this energy, we've got experiments performing at this energy, and we don't find it.
Yeah.
So it's back to the drawing board. But, like as Paul Dirac's point, the golden age of physics, 1900 and 1930s, plenty of raw data to work with. Well, what is the difference between maths and physics, right? Physics is supposed to be about, let's take Einstein's for a moment, an independent reality.
Yeah.
It's the job of the scientist to investigate it and to sort of work it out, right? But if there's no data and people are speculating, now, mathematicians, if quite honest, they do mathematics. They're not bothered about the real world. They just speculate, and they just, that's their job. It's very abstract. Physicists, including theoretical physicists, are supposed to be investigating the world about them, right? And sometimes speculation is just actually mathematics.
Yeah.
If there's no data to sort of pull back the sort of wider speculations
Right.
or sort of, inspire people. So I think, actually, I don't think it's vested interest. I think just people think, actually, it might be more interesting.
Anyone else over there? Yeah.
Thanks. Sorry, I'd like to make a comment and then ask a short question. You reminded me somehow tonight of James Joyce, and I'll tell you the reason why. The word quark, as we know, came from one of Joyce's works, The Dubliners, and his most famous one is Ulysses. And this is where your book comes in, because having read your book, and it was a fabulous read, when I got to the last page, I realised I had to start it all over again. Right? Because as much as I learned, I was also as much confused. And it's one of those things, like Ulysses, everybody says they read it, but very few people can tell you that much about it. You have to read it twice. Right? Now, in your book, you use the analogy of a ladder when you're talking about electrons. Right? The bit I haven't quite gotten yet is, we understand that it can occupy a specific state. How does it get the energy to move to a different place? Or what creates that momentum? Who decides the electron is now going to move from one state to another?
It's a very good question, because I'll try and be as brief as I can. When Bohr originally came up with his fix for the Rutherford atom, i.e. that actually there were only certain permissible orbits, he'd made them discrete, if you like, these discrete orbits, these steps on a ladder. One of the things Rutherford turned around and said, well, how does the electron know when to jump, right? And everybody's heard that Einstein says, God does not play dice. And they think, Einstein was hung up on the probability of quantum physics. Rubbish, right? Einstein was a genius at this sort of catchphrase, right? The God does not play dice is his his way of just saying, look, I don't like this. I have issues with it. Not that I have issues with probability so much. It was the reality, the nature of reality that it really got to him about the Copenhagen Interpretation. Because the man who introduced probability into quantum physics, even though I talked about Max Born and the wave function, churning out, once you manipulate it, probabilities of the outcomes of experiments, the man who introduces probability first and foremost into quantum physics is Albert Einstein in 1916. He's the chap who introduces probability because he says it's just probabilistic, if you like, when an electron jumps up and down between these different energy levels, these orbits in a hydrogen atom. Okay? So it was Einstein who introduced probability into quantum mechanics, right? The thing is, so first of all, one, it's probabilistic, right? Secondly, when I was talking about a light being shone on a metal surface, for example, well, a photon of light is absorbed by, say, a hydrogen atom. It's really being absorbed by the electron. If it's got enough energy, those rings I drew, if it's got enough energy that takes it from this, that allows it to jump the gap, if you like, it will jump the gap. And once it's jumped the gap, and if it falls back down, it emits that energy. Yeah? So that's sort of, first of all, it's probabilistic, and it sort of comes from outside as well.
Probabilistic, I think probabilistic in physics is always used as a cop-out there.
Probably.
Because
Probably,
when I can understand where Einstein was coming from to start with. If you can see it, measure it, look at it, hold it in your hand, you know where it is.
I think Schrodinger's cat.
I
What I
think
got from the Schrodinger's cat experiment was what he was saying was there was a solution of prussic acid in the box, and it was going to be a single disintegration of a single radioisotope was going to break open the vial, and you could never predict whether that it could happen never or in the next second. You could never predict when that moment of disintegration is going to happen. And you can do it statistically if there's a lot of them, but you can't do it if it's a single one, and that's the essence of quantum physics, isn't it? In many ways, the lack of capacity to predict. You see, and all science should be about.
Well, the thing is,
because mathematicians are supposed to come up with equations to predict things, you know, and they could never actually. That can never be predicted.
Well, in
right?
quantum physics, you can predict the unpredictability, if you like.
Yeah.
I mean, that's what the wave function does, and
that's pretty clear cut. All right, thank you. You can predict the unpredictable.
Yeah, you can. You can say there's a 30% chance that the particle will be over there.
Yes, it's a
right?
probabilistic.
It's a probability.
Odds really, isn't it?
So in this room, if you wanted to say where something was, you can calculate the probability it will be there rather than here. So that's a definite prediction.
Yes, but you can't be 100% certain.
Exactly.
Any more questions for Manjit?
I studied physics briefly in Canada in 1960, and the main thing I remember from 1960 in Canada is the professor said 80% of what he was teaching us was wrong. And that sounds like what you're saying today, too. No offense.
I'm just giving you the history of the development of quantum physics. I mean, these people struggle. I mean, if you look at the picture I put up at the very beginning of the 1927 conference, I mean, I'm genuinely serious when I say I can't think of another gathering of scientists or thinkers that compares to that. That concentration.
As good as it got.
It's good as it gets.
Or as good as it may ever get. As well.
Einstein, 30 years, him and a Bohr debated the nature of reality in quantum physics. What was it saying? So, and that debate has sort of been reignited in recent times. The 14 interpretations of quantum physics.
Yeah.
But people are happy with the mathematics. We make it work in terms of the things it produces, right? But in terms of what is it saying about reality, what's the next step forward, or experiments at the LHC? Most of it is. Part of it is guesswork. Part of it is people theorising about...
But is it true, Manjit, to say that it's still not possible to say why things are the way they are in this quantum world anyway? Well, and you end up with opinion. And you end up with 14 different models for it. So we're stuck with this sort of range of options still, with no definitive answer. Doesn't that seem to be the case? So.
I mean, ultimately, things are the way they are because they were the way they were.
But if you're a biologist, the big question was, what's a gene made of? Yeah. And Schrodinger was the first to say it had a physical entity. And then they found DNA, and they found genes made in these nucleotides. And there was an answer to that question, what genes are made of. But it seems to me in the world of quantum physics and theoretical physics, you still can't give definitive answers. Or at least you end up with options, and then you end up with people voting and putting their hands up.
Well, there is an element of that.
Yeah.
There is an element of that. But people are, no one is questioning, for example, the validity of the mathematics of quantum physics.
Or the observations are still sound.
And the observations and things like that. What people have, different philosophical interpretations of what it's telling them about the nature of
and yet there's a huge hunger, isn't there, for people to understand this world and come up with their own rationale to explain matter and the existence of matter and all those things.
And this is why this experiment at the LHC, for example, and there are others. There are experiments being done in the Antarctic, with neutrinos and ice telescopes. There's a whole host of experiments that are being performed in mines for searching for dark matter and what have you. And that's the search for data, if you like. The raw data that people can move forward in terms of evaluating some of the sort of competing theories that there are. And people are very optimistic at the moment. There seems to be this sort of era at the moment where actually loads of experiments that have been in the pipeline, if you like, for quite a long time, all beginning to come to fruition around the same sort of time.
A couple of months ago,
years.
there was an American lab thought they'd seen dark matter for the first time, wasn't that right? And they were looking, again, it was a statistical thing. And
that was statistical. Yeah, that's right. But again, the checks and balances have to be done. So,
anybody else? One last one, actually, because I think we'll wrap up with this one.
Somebody with a philosophy background, hearing your own voice is strange. You made a point about Schrodinger. You used the term "a bit dead," referring to the cat. Are you using that as a definite indication of a non-binary truth value? Quantum physics is used as experimental evidence of disproof of the principle of the excluded middle. So as somebody, who's coming from both science and...
All Schrodinger was doing, and the reason I phrase it like that, and the reason the Schrodinger's cat is actually a very sort of vivid thought experiment, is because, from a cat is either dead or alive, right? Most people would say, I've got a cat, Joey. He's like 3 years old. My 2 boys love him, right? But, one day he's going to be, he's either dead or alive, But the thing is, if he's in the box, if your cat's in the box, right? Einstein is, very certain. Schrödinger, it's dead or alive. Most people, and common sense would suggest that there's a cat in there, it's dead or alive. But the Copenhagen people, forget the excluded middle for the moment, they say there's a whole range
of states,
yep. And possibilities. Yeah, possibilities, not actualities, but possibilities with probabilities attached. And why I'm saying by a bit was meaning a little probability, right, as opposed to a large probability. That's what I mean by a bit dead, right? But they're all in there. There's this sort of purgatory. Until you open the box, i.e. do the measurement, right?
But again, that's a philosophical question, isn't it? To me, it's not a scientific question. That's what strikes me.
That's the point. It's when you talk about the thing of physics is giving answers about the questions of reality. I mean, it is explicitly metaphysical.
But can I just say one thing here? The debate between Einstein and Bohr, yes, it is philosophical at the end of the day, but it had real consequences, right? Because for 30, 40, 50 years, people did think that Bohr had won the debate. And part of that was because he had missionaries. If you're a postgraduate student or you're just beginning your career, you're not going to be telling Heisenberg that you're wrong about the Copenhagen interpretation of Wolfgang Pauli or any of these people in positions of power and
that
authority.
Was Gell-Mann's beef, was it?
Well, no, but that part of it, these people were able to brainwash, if you like.
Yeah.
But for Einstein, he had a different take. But he didn't sort of propagandize about it in that way. But he's also an isolated figure towards the end of his life.
Yeah.
Yesterday's man and stuff like that. So even though it's a philosophical debate between two people, some people would say, well, there are issues that are unresolved. If people have thought a little bit more about them over the last 30, 40, 50 years, then, it might be further along.
And just to finish, Manjit, what would Einstein make of the Large Hadron Collider or all the activity that's going on at the moment? And I just said there is a real feeling in the last 3 or 4 years that new data will emerge. Isn't that right? Do you think he'd be...
Well, Einstein was an interesting fellow because I said to you when I was talking about his quantum theory of light, he had a look at what Planck had come up with, was dissatisfied in Planck's derivation of it, thought it was a little bit iffy, came up with his own by basically saying, okay, I'm going to treat light as particles. And I've got the same equation. So I've got an equation, and it's logically consistent.
Yep.
Now, I've got this. Let me see if I can apply it to some existing data, the photoelectric effect equation. So in a sense, Einstein liked data,
yes,
in that sense. He would have liked data, but again, he was more driven by ideas and then testing them out with the data that was available.
Right.
Do you know what I mean?
Yeah.
He wasn't one of those people who thought, let me take this bit of data and explain that.
Well, maybe let's hope he's a bit dead. Thank you, Manjit, for